we are joined now on the line by Dr. William O'Connor, who is the Associate Professor from UCD. Good afternoon, William.
Good afternoon, Sean. How are you?
Really good. And yourself?
Great, thanks. Great.
Good.
Thank you for joining us.
Absolutely.
You're very welcome.
Well, you're on to talk to us particularly about AirSat-1, which is a really interesting project that's going on at the minute out in UCD. I suppose, could you maybe give us a little bit of a background for people who maybe don't know what the whole AirSat-1 project is?
Okay. So, it's the first Irish satellite, so that's exciting and historic, which is being built in UCD mainly by students. So it's a student-led project. Well, when I say students, these are postgraduate students, mainly people doing masters or doctorates. And it's organised or sponsored in some way by the European Space Agency. So Ireland is a member of the European Space Agency. Mm-hmm. You'll see the little Irish flag on the side of the ESA rockets and so on. Oh. So we're there, and as part of their brief, ESA's brief, is education in space. And under this program, they assign some of their budget for this. One of their programs is to invite people to put a satellite into space. So we're building the satellite, and the European Space Agency will take it up to the International Space Station and launch it from there. Now, that may sound, I don't know what it sounds like, but to say it's a lot of work.
Yeah, definitely.
Now, it's a very small satellite. It's technically known as a microsatellite or a CubeSat. And this is a change in the space world. Traditionally, satellites were often very big, very expensive, could take 10 or more years of development of big teams. Recently, the tendency is to go for more satellites, but much smaller, and use off-the-shelf commercial components as much as possible. So that makes them cheaper, easier to make, and cheaper to get into space. So our satellite is an example of that. Mm-hmm. So we're calling it AirSat-1, EIRSAT, which is a slightly clever name. The EIR, well, besides being for Ireland, it's also Educational Irish Research Satellite.
Oh, I thought it was just for Ireland. I like that.
Well, it's both.
Yeah.
And we're calling it AirSat-1 because we're hoping it won't be the last. So we're trying to develop expertise to do more of this in the future. Yeah. And in fact, if you can go on the internet and look up AirSat-1, EIRSAT-1. There's also Twitter, and you'll find more information. So people who are interested can find out more, and photographs of the students who are involved and so on. Now, so the plan is, well, it's all supervised by a program within ESA called Fly Your Satellite. Yeah. So over a year ago, nearly 2 years ago, some people in physics in UCD, the physics department, made a proposal. So the European Space Agency invited people, said, well, we'll put your satellite into space for you. We'll launch it if you do the right thing or what you propose. So a proposal was made and it was accepted. So that's what's got us started. And as I said, that was nearly 2 years ago now, and since then we've gone through a long, detailed process of designing the satellite. Now it's got three experiments on board, original experiments, all designed in UCD, and then in addition it has everything an ordinary satellite needs. I'll just explain. Well, first of all, you may be imagining a big thing. This is all the size of a shoebox, even a small shoebox.
Oh, wow.
Or your litre carton of milk, a little bit bigger, somewhere around that size.
So it is quite small.
Yeah.
So it would fit in your rucksack if you were carrying it around.
Wow.
Handy.
But if it's small, it also needs everything on board that a bigger satellite would have. So it has to have radio communication. We need to be able to talk to it. It has to have an onboard computer controlling things. It needs power supply, so there's solar panels to get power from the sun and power up, to charge up the batteries.
Oh, very good.
It has what's called an attitude control system. Attitude is what the space people use to describe just direction controlling, because it needs to point in a certain direction.
Yeah.
And that needs a control system. And there are a few other things needed on board. So it's a complicated little piece of machinery. And because it's going up into space, there are all sorts of special requirements on it. And because the European Space Agency is going to kindly take it up in one of their launchers, which is going up to the International Space Station regularly, so they take up food and supplies and oxygen and astronauts who are they're permanent people living in the International Space Station, as you know. So we're going to hitch a ride on one of those service missions, and then the astronauts on board the International Space Station will shoot it out later on. So because they're doing all that for us, the European Space Agency follow everything very, very closely, because they don't want to take anything up to the International Space Station that might give off funny vapors, or
of course,
the batteries start overheating, or the radio comes on when it shouldn't and interferes, and so on. But also because they're supporting us, so they want to make sure we do it right. So we have the benefit of having all their experts checking everything we're doing as we're going along. So that's where we are at the moment. There are a number of milestones along the way. A few months ago. Yeah.
Sorry, no, I was just going to say, you mentioned earlier on, I didn't want to stop you in the middle of your flow,
Sure.
But you mentioned earlier on, talking about how it's gone back a bit, but talking about how making this, it was done using kind of more off-the-shelf parts and stuff rather than specialist parts.
Yeah.
Which has got to be fantastic, I say, for people who maybe will be looking to get into this field sort of down the road, or maybe they're at home and they're sort of wanting to kind of play around with it because they know in future this is a field they'd love to get into and love to be kind of a part of, where they know they could actually go and find these parts and possibly they'll get an idea of how to build this kind of stuff themselves.
Sure, yeah. It would... Perhaps the most expensive thing is getting this thing up into space.
Yeah.
But actually, the building part of the satellite, the components that every satellite needs, are what are available off the shelf. By commercial off the shelf, I mean there's quite a few companies, maybe half a dozen companies, certainly around the world, who will design or sell you. Say the radio communication side of it, the onboard computer side of it, the electrical power control side of it. Those things are on printed circuit boards that you can buy, and then you can put them into your satellite. So typically your satellite might have something special on board, but you still need all these other things which are standard. And so now, when I say cheap, we're not talking small money. I mean, each of those things, well, you can go on the web of the different companies and see they'll even have a price list there. But
we're talking relative, I suppose, in comparison to some of the massive satellites that are up there now. It's relatively inexpensive.
So each of those components might be costing you 10 grand, 15 grand, that sort of money, as opposed to hundreds of grand. Because of the standardization makes it much more economical.
Yeah, absolutely. So in terms of, once it's up there, you obviously there's a particular mission you're aiming for here. There's stuff you're kind of going for. What's the overall goal for AirSat-1?
Good question. Right. Well, there are 3 experiments on board, which are novel, new, designed in UCD. The first one is to detect what are called cosmic ray bursts. Now, what are they? Well, it turns out that there are bursts of cosmic radiation, which is electromagnetic radiation, coming from very, very far away in the universe, which are very bright over a very short time. So it's like a flash. say short time, it lasts maybe 10 seconds, 12 seconds, which in astronomical terms is very short.
Yeah.
And this is very, very powerful radiation, which hits and then goes away. Now, they were only detected first when people went up into space or high altitude, because the atmosphere shields us down below here. And in the physics department in UCD, they've developed a new kind of sensor detector to detect these cosmic ray bursts, which is a special crystal which scintillates, or it produces light when the cosmic rays go through it, and then you detect those flashes of light, the photons of light, and that's the way you detect this cosmic ray burst. And this is a new kind of sensor in that it's lighter, it's low voltage. It's the previous sensors were high voltage vacuum tube type things, which were expensive and awkward. So that's one experiment, detecting cosmic ray bursts. The second experiment is testing out some coatings which were developed by an Irish company called InBio. These are coatings that the European Space Agency is going to use on a satellite to go around the Sun, Solar Explorer. And these coatings are protecting the satellite from the radiation of the Sun. So they're heat protection mainly. And obviously they've been fully tested on Earth in ovens and vacuums and so on, but not in space. And the space environment can affect the coating in some way. So we have on board, we have 4 samples of the coatings, 2 black, 2 white, and they are going to test those coatings. So that's the second experiment. And the third, if you're still with me,
Yes,
absolutely.
yeah.
which is the one I'm most interested in or most involved in, which is a new way of what's called attitude control, which means we've to control how the satellite is pointed in space. So when it comes out of the International Space Station, it could be tumbling, head over heels. So the first thing is to stabilize it, stop it tumbling, and then we want to point it in a certain direction so that we can make the measurements and get the right amount of solar power and so on. And we have a new way of doing that, or calculating what's needed. I don't know. You want me to go into details there, but how are we controlling the attitude or direction? Well, that's an interesting story, because there are coils in the satellite. We put current through the coils that creates a magnetic field, and that interacts with the Earth's magnetic field.
Yeah.
And that's how we get turning action, or torque, as it's called. But we have to work out what current to put in and when. And for that, the calculations are somewhat tricky. So that's what we're working on.
Sorry, just obviously there's going to be an awful lot of data coming back from the satellite. Is it going to be a matter of when it comes back, like if it comes back to Earth, is that how you'll be analysing the data, or is it when it's overhead, or where does the data analysis come in?
Fantastic. Very good. Okay, so another aspect of this whole thing is building what's called the ground station. So on the roof of the building, a physics building in UCD, we are going to have a big antenna, which we hope will be picking up the signals from AirSat-1. Now, we can only start picking up signals when it's over the horizon. So we had to do calculations of how much it's going to be, or for how long, and that depends on the orbit. So, and how much data we can get down is determined by how quickly we can get the data and how long we can talk to it, how long it's above the horizon. So we're reckoning about 29 minutes every day. So we have a window when it's above, and our antenna aerial will have to track it, point towards it, and we'll know where it is. And to get the maximum amount of data, we point the antenna towards it, and we hope that'll give us all the information we're looking for.
Amazing.
Fantastic.
And that's, nearly half an hour a day. I thought it would be kind of every few weeks or something that it'll be passing over, but that's great that it'll be daily.
Yeah, well, the orbit takes about 90 minutes.
Oh.
So So it goes the whole way around the world every 90 minutes. So it's going
Wow.
pretty fast.
It's extremely fast.
But that doesn't mean it's over Ireland all the time, because obviously it's and the orbit is at a funny angle. It's you might imagine it first as going around the equator, but in fact the International Space Station orbit is at quite a sharp angle to the equator. So it goes up fairly near the North Pole and then fairly near the South Pole.
Very good.
So and ours will be doing more or less the same orbit.
Wow. So what kind of speed would that be? Or do you know?
It's of the order of 30,000 kilometers per hour.
Wow.
So pretty fast.
Yeah. You get stopped by a speed camera going that.
Yeah. Don't try that on the M50.
But that's incredible, and so it's essentially, as you said, it's following roughly the orbit that the space station will be following.
That's right.
And you were talking as well a little bit earlier about using, in terms of navigation and stuff, using the Earth's magnetic fields. Or
that's right.
Is that kind of due, in terms of the fact that that's what you're using? Is that just kind of because it's the best source of that, rather, because obviously in space there's no real up or down, so sort of to navigate yourself. So is it kind of like the Earth is just sort of your anchor point essentially?
Well, there are a few reasons for doing it. There are a few ways you could control your attitude, as it's called. One would be to have little rockets or thrusters, so you fire them to move yourself around. But they're heavy. You have to have fuel. You can run out of fuel, and you have to do all sorts of calculations. So because this whole thing is very small, we wanted something that was light and low power. And the coil idea, the magnetic coil idea, means that we can use power which we're getting from the sun through the solar panels, which are charging the batteries, so that you can use electrical power. There are other ways of doing that, things called reaction wheels, where you spin little wheels on board, and the reaction gives you a turning action. But again, there's a weight involvement there, and mechanical rigidity, reliability, and so on. So these are called magnet torquers, which is compression of magnetic torquers. They're the simplest. Now there are a few problems with them. The amount of turning action is tiny. I mean, think of your compass needle swinging in the Earth's magnetic field. There isn't much turning action going on there, and the needle is very, very light. Our thing is a bit heavier than the compass needle. So the amount you can get of torque you get is very small. That's one problem. And then the Earth's magnetic field, because the orbit is going up near the North Pole and the South Pole in 90 minutes, or 45 minutes each, it's changing continually, so that's part of the complication. So it's an interesting problem, but it's the best if you want something that's cheap and light.
Yeah. I think it's amazing that something so small is able to gather so much, do so many experiments, and is going to be so useful. But as you said, it's maybe a little bit smaller than a shoebox or bigger than a carton of milk.
That's right. But if you think of how much is on your mobile phone...
very good, actually. Yeah, I kind of never thought of making that comparison. You're so right.
You have an onboard computer there, and you have apps and all sorts of tricks and so on. So that's the electronic revolution. You get more and more and more into smaller and smaller
tiny
spaces. So we're taking full advantage of that in the satellite design.
Yeah.
That's amazing. Oh, I'm so excited to hear all. I'm definitely going to be keeping up with this one.
Well, it is very exciting.
Yeah.
And
that's from Ireland.
Everybody is learning an enormous amount.
Yeah.
I mean, I'm learning, and it's the students who are doing the work. I want to emphasize that very much. So there are some older heads like me, staff, who are involved in supervising and guiding a little bit, but they're doing all the real work. The designing and building and testing. And if you go onto Twitter, you'll see photographs of the students working. Some of the times they're wearing funny clothes because they have to go into what's called a clean room. There's a special room. The satellite will be assembled in a clean room where it's minimum dust because dust can cause problems like electrical connections and so on. So there's a controlled environment, a clean room environment, and that means you have to put on special clothes so that the hair or fluff or whatever from your head or from your clothes doesn't add to the dust in the room.
Yeah.
So there are just so many aspects of this whole thing that it's only when you start doing it you realize there's a lot of work and a lot of different kinds of work and different things to be thought about for it all to come together. But it's great fun. It's very exciting to be involved. It
does. It sounds absolutely incredible, to be honest. And as Orla said, kind of proud as well of the fact that we're getting out there. You know, like we've spoken on the show to the likes of David Moore we've had from Astronomy Ireland on, and he mentioned AirSat 1 and how the kind of the Irish astronomy community and space community, the science community in general, are very excited about what's going on with AirSat 1 and the fact that
there's what a large community as well in Ireland for a small island like.
That's right. And well, there are a number of companies in Ireland involved in different aspects of the space industry or making certain components, certain parts, say for rocket launchers and so on, but and the electronics end and data. But this is the first time that a complete satellite has been designed, built, tested, and operated by a group in Ireland. And part of the purpose is to educate students in this whole area so they can go on and then be employed in the space industry or maybe set up their own space industry because there's now scope for that. So space has now moved on to some extent to more commercial applications of space. So there are companies now getting involved in space as a commercial enterprise, as opposed to in the past it could only be big countries with big economies that could do this. And CubeSats is part of that story. It makes it possible for smaller industries to get involved.
Yeah.
Absolutely. And we're going to have to wrap up now in a second. I don't want to keep you here all day either, as much as we could talk about this for hours. It's fascinating. But the whole, you mentioned as well, was it the Flyer satellite program?
That's right.
So there is a few other nations in getting involved with the CubeSat thing as well, am I right?
Oh, that's right, yes. And, well, our neighbours in the UK, there are programs there, but across Europe, So we're not the first or the only one by any means. And just to say that the European Space Agency was set up over 50 years ago. They recently had their 50th anniversary, and in their foundation, one of their purposes was education in space, and they take that very seriously. So they allocate a budget for it. A big budget, part of their budget is for education, and so this Flyer satellite program is part of that educational purpose or role that ESA is to educate future space scientists.
Amazing. Absolutely. This is so exciting. I love this.
It is. And we'd love to have you on again in the future as we kind of get closer to launch and stuff like that, and just get a bit more information of what's going on. We'd definitely love to have you back.
Certainly.
Thanks
my pleasure.
So much.
I can do that.
Brilliant. Well,
or you could talk to somebody else on the team if you wish.
Absolutely. We just, as I said, we'd love to just get more information on it and find out everything that's going on. But
very good.
Dr. William O'Connell, sorry, what were you saying? Sorry.
I just got to say, before you wrap up, have a look on the web under AirSat 1 or on Twitter, and you will get more information there, and so people who are interested can find out more background things I haven't mentioned or haven't explained properly. They might be able to get a better picture there. So
people can follow what's going on all your social medias. I assume just look for AirSat 1.
Exactly.
Brilliant.
Perfect. Thanks so much for coming on.
Delighted. My pleasure. Thank you for having me.
No problem.
Cheers. Thanks very much.
Have a lovely day.
All the best. Bye.
Bye-bye.